Good evening, students. In the last class, we saw how we can able to express the Lagrange's equation in terms of the flexibility, and that is influence coefficient and stiffness influence coefficient. So that formulation is very general, and for a very specific case, we took one example and saw how we can able to obtain the flexibility influence coefficient for 3-degree of freedom system, and also the stiffness influence coefficient. We observed that the stiffness of flexibility coefficient is relatively easier to obtain. We obtain that using first principle by relating the deformation and the force or the torque, corresponding torque. But stiffness coefficient also can be obtained directly if we derive the equation of motion using whatever the method we have learned, Hamilton principle or Lagrange's equation. So stiffness influence coefficients are relatively easier to obtain. Today we'll continue some more concepts, especially because we have seen that a particular system, sometimes we have a choice of different coordinate set to be chosen. So we'll be deriving today some general transformation matrix, and for a very specific case, maybe in the next chapter we'll see that such transformation matrix will be leading to so-called modal analysis, which is used in vibrations. There is very specific transformation, but today I will cover something more general transformation, which is applicable for any one set of generalized coordinate of a system to another generalized set of coordinates of the same system. So if you're choosing a different coordinate system, there is no need to rederive all the derivations. Just by transformation, we can get the equation of motion in a new generalized coordinate set. Using this transformation, generally the form of the equation will change, like mass matrix and stiffness matrix will change, but final characteristics of the solution will not be changing because system is same. So the same natural frequency and other things will be getting from the different set of generalized coordinate, but often sometimes is convenient to use one set of generalized coordinate as compared to the other. So with this background, let us see what we can, the slides I can show you now. So the linear transformation. So this is valid for two sets of generalized coordinate which are having some kind of linear relationship. So this is not, we're not dealing with the nonlinear relationship between two generalized coordinates sets. So here we expressed earlier the kinetic energy in terms of the mass coefficients, and we have seen that this mass coefficient depend upon the system masses, set of masses, and their symmetric in nature. Similarly, the potential energy is expressed in the form of the stiffness flexibility coefficient Kij, and which are related with the system stiffness as we have seen in the previous example, and these coefficients are also symmetric. And so now we want to relate the coordinates Qi, which we have been using it, to another set of generalized coordinate. This is eta r. So eta r, qi, we have I is equal to 1 to n. So n number of generalized coordinates we have in the first case. Second case, for the same system, if we are choosing a different set of coordinates, let us say eta r, where r is from 1 to n, and we have relationship between these two coordinates, because generally the coordinates are related, like we have the rectangular coordinate and the polar coordinates. So they're related, x, y, and r theta. So they are related by some geometrical relationship. So we let us say those, whatever the coordinate we are choosing, are having some uh, linear relationship. So qi is summation of some beta. Beta is a constant, and eta r is a new generalized coordinate we want to use. So you can see the beta is having the subscript I and r. So if we take this one of them, so on the right side we have n number of terms, and they are summed up. But this I can take value from 1 to n. So such we have n number of equations. So we can write this for q1, q2, like that up to qn. And in each of them, we have n number of terms in the right side. So you see that there's some kind of simultaneous equation, and simultaneous equations are there. They can be put, all of them, all the n equation in a matrix forms like this. So q, which is containing all the generalized coordinate q1, q2 to up to qn, is related with the eta 1, eta 2, eta 3, eta n with beta. So beta is a matrix which is having size n into n, where n is the number of degree of freedom system, or the number of generalized coordinate. And here you can see that beta will not be symmetric in general, unlike in the case of mass coefficient or the stiffness coefficient. This is a geometrical relationship between these two generalized coordinates. So not necessarily this beta will be symmetric. So this is important to note, that beta IR is not equal to beta RI. And these will be generally constants. Beta will be, generally it will be constants. So that previous equation, if we derive or take derivative with respect to time, we can get the velocity of the generalized coordinate. And because beta is constant, only the derivative in the right side will be of the eta. So we are derivating this because we need them in a kinetic energy. So kinetic energy we expressed in terms of the mass coefficients, and these are the velocity qi dot and qj dot. So here we can substitute this equation, taking care of that, because we are product of two quantities. So we are taking two dummy variable. One is r and another is s, to while substituting these two equations here, so that we have all the terms related to the various products. So you can see that mass coefficient is same, but this is, we have substituted for qi dot, and the another one is we have substituted for qj dot. Now if you see, we can able to reshuffle the summation sign, summations. So because mij is independent of r, so it can come inside, and those terms which are not related with so you can see here beta and eta r and eta s are independent of this ij. Here even we reshuffle the summation of the ij inside the rnj, and rnj is outside. So reshuffling we have done, and because eta r and eta s are independent of ij, so it can come out from the sign of this. So we want to change the summation order. And once we did this, the term within this box, we are representing that as capital MR, capital MR, and eta R, eta S is as it is. So actually we want to write this expression similar to the form of the original generalized coordinate, in which mij was there, qi and qj dots are there. So here this also is a similar form of the previous one. Only thing is now the new generalized coordinate eta r dot and eta s dots are coming, and whatever the terms, other things we are representing as a capital rs. So just to distinguish with the small mij, here we are writing mrs. And r and s are dummy variables, so again we can bring back because once we have this form, there are two summations. We can always change the dummy variable to any variable. So again, we can write them in this form. So anyway, here if you see this mass coefficient and the previous mass coefficient, they'll be different because they're related with this expression. So the mass coefficients are changing with respect to the generalized coordinate chosen. So it indicates that when we are taking another set of generalized coordinate, the form of the mass matrix will change. The various elements of the mass matrix will be changing if we take a different generalized coordinate. This is for the mass matrix. Same thing we can able to do with the potential energy and the stiffness matrix we can obtain. So this inertia coefficient is depending upon the or new generalized coordinate depends upon the beta, and obviously the beta is implicitly related with the eta because that is the relationship between the previous generalized coordinate and the new generalized coordinate. So this is for the mass coefficient or inertia coefficient. Same thing we can do it for the potential energy. We express potential energy in terms of the stiffness coefficient, stiffness influence coefficient. And now again we can put the qi and ji here, and we can reshuffle this. I think this should be eta. This should be eta because now we have directly changed the coordinates. So here I have not shown the intermediate steps. Directly I have shown the final form of this because once we substitute for qi and qj, again reshuffle, we can able to. So here KRS, capital KRS is related with the small rs. Capital KRS is related with the k, small k ij, like this, with the whatever the transformation coefficients are here. The form of this is similar to the mass coefficient. So here also in the new generalized coordinate, the form of the stiffness coefficients are changing, but these are symmetric for the new coordinate also because it was symmetric for the previous coordinate also. So going back to the this transformation which we define, which we wrote in the matrix form. Here if we, so this is the same matrix form, and if we differentiate this with respect to time, which as we did previously, we will, because beta is a constant matrix, so eta dot term will be getting. And here now we want to, because in the kinetic energy, we have term of the q dot transpose, or in the potential energy, we have term of the q transpose. So from the previous expression, if we do the transpose of this, so the order of the matrices will change, and then the transpose of each of them will be there. As I mentioned earlier, beta is not symmetric, so beta and beta transpose are not same. Like K and M are there. Similarly, if we do for Q dot transpose, the order of the matrices will change, and the transpose of each of them will be there in the multiplication form. So this is the kinetic energy in the terms of the one generalized coordinate Q. Now we are substituting Q dot this transpose from here. So I got these two terms. Mass matrix is same. Similarly, Q dot I am substituting from the previous expression. So this. So you can see that now the kinetic energy is there in terms of the new generalized coordinate, and there are some matrices in between which is there in the box. So mass matrix of the previous uh, generalized coordinate pre-multiplied by the beta transpose and post-multiplied by the beta. Beta is the transformation matrix. So this box thing I'm writing as a capital M. So if I write like that, then this expression is simple. You can see that is the kinetic energy in terms of the new generalized coordinate, where the capital M is now a new mass matrix, and new mass matrix which I have taken here is defined like this. Okay, so it's defined like this. Similarly, for potential energy, we can substitute for Q transpose and Q from previous expression. So we will get a K post and P multiplied by beta, and that can be defined as capital K. So capital K is related with the small k like this. So small k is stiffness coefficient for the Q generalized coordinate, and capital K is for the eta, a new generalized coordinate. And here M and K are symmetric, as we had the small m and k symmetric. So we have taken care of the kinetic energy and the potential energy. So for virtual work expression, which we had written earlier. So Qi is the generalized coordinate, and delta Qi is the virtual displacement of the original generalized coordinate. Now we want to transform this also in new coordinate, that is eta, and so we had the relationship between the Qi and the eta. So if we take the variation of Q, because beta is constant, so only the variation of the eta will take place in this transformation. So this we can substitute in the virtual work. So if we substitute in the virtual work, so instead of beta or this variation of Qi, this within the bracket term will come, and then we can able to change the order of the summation. We can keep the R outside, so this can be rearranged like this, and within the term, within the box, whatever the term is there, that I'm writing as a capital NR. So capital NR is a new generalized forces. Earlier it was capital Q, now it is capital N, and NR is defined by the term within the bracket, which is written here. So now you can see the new generalized forces we have expressed in terms of the old generalized forces with the help of those beta coefficient of the transformation matrix. And n r can take value from 1 to n. So this we have n such relationship. So what we can do, we can write this expression for r is equal to 1, 2, 3 like that, and all of them if we combine in a matrix form, so this will be like this. where n contain n1, n2, n3, n4. Capital Q contain Q1, Q2, Qn, and beta is the transpose of that. Okay, because here the R which is there of the n in the beta is in the second subscript, so that's why the transpose of the beta is coming here. So this is the general relationship between the new generalized force and the old generalized force when we transform the generalized coordinate. So now we are transformation for the mass matrix, for the stiffness matrix, and the force also. So that means now we can able to transform the whole equation of motion also in the new generalized coordinates. So this is same thing as the previous one, this one. So this we are writing in a matrix form. So this has been written in the matrix form. Here, as we have related earlier also, this relationship. Now, the equation of motion, which was earlier, we had the small m q double dot plus small k, q is equal to capital Q. So that will change to this form where capital M is defined as with the previous mass matrix, K with the previous mass matrix, and the new generalized force with this. So this is the equation of motion of the system in the new generalized coordinate set. So you can see that just by transformation like this, we can able to get the new equation of motion in a new generalized coordinate. So there is no need to rederive all the expressions and can be transformed in any other new set of generalized coordinate. So, but this transformation which we have defined, which is beta, so is having n into n components, and so that is Bij. So choice of this coefficient will decide what will be the form of the mass matrix and the stiffness matrix. So we can choose this coefficient as that maybe the new generalized coordinate, the mass matrix, which is earlier fully populated, all the elements are there in the mass matrix, even the diagonal term and off diagonal term. The new set can have the only diagonal terms. So if a matrix is having only diagonal terms, then the solution becomes easier. So, but choice of this, we'll see how we can able to choose such transformation which will make the mass matrix all the off diagonal terms 0. Only the diagonal terms will be there. Or even we can able to do transformation which will make the stiffness matrix either that also all the off diagonal terms equal to 0. So there is very specific case in which we can able to do not only the mass matrix as well as the stiffness matrix off diagonal term 0 by choosing a new set of generalized coordinate. So that will be a very specific case, but that is possible. Maybe I think once we'll go in the next chapter, we'll see how we can able to obtain such transformation, which will make the mass matrix and stiffness matrix diagonal. So here, this has been written. The mass with this sign is representing that is having only the diagonal terms. K is also having the diagonal terms. But as I mentioned, that will be a very specific transformation matrix. In that case only, this is possible that we can have the mass matrix as well as the stiffness matrix containing only the diagonal terms. And generally, that specific case, the generalized coordinate itself is called natural coordinates or principal coordinate normal coordinates. So these they're all representing same coordinate system, but there is a coordinate system. If we transform, we will get the mass matrix and stiffness matrix diagonal. If they are diagonal, what will happen? If we take the first row of this equation, or the ith row of this equation, or rth row of equation, all will be independent of each other. So like this one, this the rth row of this will be of this form. So if you see, this is something mass, this acceleration, stiffness, displacement. So is something like mx double dot plus kx is equal to force. So this similar to the single degree of freedom system equation it looks, and they are n in number. So all equations are independent of each other, and is something like all equations are uncoupled. There is no coupling between the various governing equations. So that is the easiest to solve, because if we have n differential equation and all are independent of each other, then the solution of that is easier. So that is the motivation of this particular specific transformation, in which we would like to diagonalize the mass matrix and the stiffness matrix, so that we can get equations similar to the single degree of freedom system, but they will be n in number, and but the solution is easier. So such transformation, which is very specific transformation, is called that is called sometime modal matrix. The beta, the form of the beta, which is called modal matrix, and we'll see that they are basically nothing but the eigenvector of the problem. So in the next section or the next chapter, we'll study the eigenvector. What are the eigenvector of the system? So that transformation, if we take as eigenvector, then such decoupling of the equations are possible. As I mentioned, when we transform a system from one set of generalized coordinate to another, generally the property of the system will not change. The natural frequency and other things will not change. So whatever the transformation we'll be dealing with, that kind of transformation will be dealing, and that is called similarity transformation also, in which the characteristics of the solution will not change. Maybe the intermediate step of the solution will change. It may get simplified, but finally the solution will be same. So if any question on this, I'll take up. Otherwise, I'll take up one example. If you have any question on this transformation, otherwise I'll take up one or two example, and then we'll close this particular chapter. Okay. So I'll take up one example on the transformation. So if you see the figure, there is a rigid bar, or the shaft is there. So deformation of the shaft is not there. This is a rigid, but this tapered. So C is the center of the shaft. So this is the midpoint of the shaft. G is the center of gravity, because this tapered and mass is more toward this. So the center of gravity is toward the right side of the center of the mass. A and B are the two ends of the shaft, where the supported by springs. And we are assuming that this particular shaft is having motion in this plane only. So this can go up and down, or it can tilt. So these two motions we are considering. So that means, what is the degree of freedom of the system? If we define, let us say, any type of generalized coordinate we can choose. Like if we choose the displacement of the center of gravity, let us say YG is the center of gravity location, and Px is the tilt of this particular uh, shaft. So that will define the position of the this particular shaft. We are assuming that this particular shaft is having no motion in the horizontal direction. Only motion in the vertical direction is taking place. So y direction displacement is taking place, and the tilt. So this is one set of generalized coordinate which will define the position of the shaft. So if we define this generalized coordinate, we can write kinetic energy, potential energy of the system. So like kinetic energy, because we have taken the generalized coordinate at the center of gravity, so we can directly write the linear kinetic energy and the rotational kinetic energy about the center of gravity, where Ig is the polar mass moment of inertia about the center of gravity. Potential energy will depend upon how much deformation of the spring which is there at end A of the shaft and at the end B of the shaft is there. So let us say YA and YB are the vertical displacement of the shaft ends, and those deformation we can able to relate with the generalized coordinate we have chosen. So YA displacement of this end can be written as displacement of G. Let us say it is tilting something like this. So YA can be written as YG minus this length and this angle. So that means this much distance. If we subtract from YG, we'll get Y. So this is the thing we have done here. And the YB will be nothing but, so LAG is nothing but the length of the shaft between A and G. And LBG is the length of the shaft between LBG. For displacement at B, we'll be having the YG plus this much amount. So that means in the here, YB is somewhere here. So YG plus this much amount will be the displacement. So we have related this, and so here you can see the Ka, the spring is deforming by Ya displacement. So square of that will give us the potential energy of the spring A, and this is the potential energy of the spring B. But we can able to replace Ya and Yb with the new with the generalized coordinate, because we need to write all the expression in the generalized coordinate only. So now you can see we have replaced this. So the potential energy and the kinetic energy are there in the our chosen generalized coordinate, that is YG and phi-g. So anyway, this we already seen in the previous chapter. Once we get the kinetic energy, potential energy, how we can able to get the equation of motion. So that steps I will not repeat here. So we can get the equation of motion from that kinetic energy and potential energy in terms of the chosen generalized coordinate. So once we have the chosen generalized coordinate equation of motion, now if we want to obtain equation of motion in a, let us say, new coordinate system. So if you see the second part of the equation, in which, let us say, if I want the equation of motion in a generalized coordinate, Ya and Px. So y is the displacement of the end A, and is tilting about that. So that angle is Px. So if this is the new coordinate system, so we can able to relate these two coordinate system with the previous coordinate system. So Yg, the same figure can be used. Yg is nothing but Ya plus Lag Px. So YG is nothing but YA plus this amount, and the angle is same. So see, this is the same equation as we used earlier. So something like the left hand side coordinates are Q1 and Q2, and right hand side are eta1 and eta2. So, and if we combine them in a matrix form, so this is nothing but the Q matrix, this is the eta matrix, and this is the transformation matrix. So this, because they are related with geometrically, so the beta matrix contain constants and related with the geometry of the system. So this is the transformation matrix for this equation of motion to be transformed to new generalized coordinate, which is ya and phi x. So to transform that, what we need to do, this mass matrix we need to post multiply by the beta. So this is the beta matrix, and pre-multiply by the transpose of the that particular matrix or beta matrix. So this the M is the new mass matrix in the new generalized coordinate set, which is now ya and phi x. So if we transpose this, we'll get this, and if we expand this, finally we'll get the mass matrix in the new generalized coordinate set as like this. So if you compare the previous mass matrix and the new one, previous one was actually off diagonal terms were 0, but now they are not 0. This is a fully populated matrix. So one reason for this diagonal is if we take the generalized coordinate at the center of gravity, then the mass matrix becomes diagonal. Because in the new generalized coordinate, we are taken at this end, which is not center of gravity. So that's why they're coupled in off diagonal terms also. Well, now let us see the new stiffness matrix. So new stiffness matrix again can be obtained. So this is the previous stiffness matrix multiplied by multiplied by the beta matrix and pre-multiplied by the transpose of the beta matrix. So if you do the operation of this and simplify, you will get a matrix like this, which anyway earlier it was coupled, now also coupled, but we are getting a stiffness matrix directly by transformation in a new generalized coordinate set. So once we have got this, we can write the equation of motion in a new generalized coordinate ya and phi x. So where mass matrix is there, and here new stiffness matrix is there, and this is the new generalized coordinate. So this is the example how we can able to transform the equation of motion from one set of generalized coordinate to another one. So here we can have several possibilities. So even if you want, let us say, the generalized coordinate to be ya and yb, those two generalized coordinates will be enough to define the position of this. So this we can able to relate this ya and yb with the phi yg and phi. So using this, we can able to develop another transformation matrix, which will transform the equation of motion from the yg phi g to ya yb. I'm giving a specific one particular assignment in which you need to transform the equation of motion in a new generalized coordinate ye and phi x. What is ye position? E is the position on the shaft. The position is given by this relationship. So the length of that particular point E from and A multiplied by stiffness of the spring in the A is equal to length of the part E from B into KB. So this is the geometrical relationship is given for point E. Now you need to obtain the equation of motion. First, you need to obtain the relationship between the the YE Px and the YG Px, and then the same transformation you can use, and you'll see that very interesting thing that you'll get the stiffness matrix in the new generalized coordinate as uncoupled stiffness matrix. So this I'm leaving it to you to do as assignment, because I already explained one step, one particular example. You can do it the second one yourself. Okay, so I'll take another example in which yeah, so this is the same I think the problem which I think we obtain the stiffness influence coefficient and the flexibility influence coefficient. So for this, we had the generalized coordinate theta1, theta2, theta3. So these were the generalized coordinate. The kinetic energy of this system for torsional case, we can able to write simply like this. And this particular kinetic energy in the previous slides we have seen in the summation form, and we have transformed them in a matrix form. So this is the similar changing the kinetic energy in the matrix form. So it will take this the quadratic form of this, where IP matrix will be of this form and theta dot will be of this form. So this is a quadratic form we have been seeing of the kinetic energy, and where the IP is the mass matrix or the inertia matrix. Same thing for the potential energy, because this can be written. I think whatever the background we have now, we can easily write the potential energy. Only thing is the in between the two disks will be having a relative twist. The ends of the spring will be having twist only the respective theta1 and theta3, but in between the two ends are having relative motion, so relative twist will be there. So this is the potential energy. This also a rearrangement can be written in a quadratic form, where theta is nothing but a vector theta1, theta2, theta3. K will take this form, which anyway, if we derive the equation of motion, we can get this similar form. So this is the so this is nothing but you can see these are then stiffness coefficients. So this is K11, K12, K13, or like that. So these are the, and we have seen that the equation of motion in the matrix form of this form, where shaft segment stiffnesses are given by for torsion case, because we are dealing with the torsion case given by this. Okay, so as I shown in the previous slide, I think this is, yeah, I think this should be I1, I2, I3. So this is the same example, but with I1, I2, I3. So this is the quadratic form of the kinetic energy, quadratic form of the potential energy, having this form. And if we take a specific case when M1, M2, or I1, I2 is equal to I, and I3 is equal to 2I. Similarly, K1, K2, K3 is equal to some specific example we want to see, so that numerically we can able to solve something. So this has been chosen so that we get a mass matrix. So outside, I think it will be having I outside will be there. Instead of M, I am saying you should be taking this as I. So mass matrix will take this form with I term outside. Similarly, the stiffness matrix will be of this form. Now, if we use a transformation beta to transform this matrices, mass matrix and stiffness matrix, let us say if you choose a beta matrix like this, where again I'm saying M should be treated as I, mass moment of inertia. So this is a one transformation matrix. At present, maybe you can don't bother about how it has come, but if you do the transformation using this matrix, you will find that the mass matrix, which anyway is a diagonal, but even the stiffness matrix will become diagonal. So this is the transformation which is doing the transformation from q coordinate, that is theta 1, theta 2, theta 3 to eta 1, eta 2, eta 3. Beta is given by these numbers. So even q, the k matrix will get diagonal. So anyway, here you can see when I'm substituting the q and q in the terms of eta, I'm getting diagonal mass matrix. And here even the mass matrix is becoming identity matrix. So you can able to check by MATLAB or hand calculation that if you substitute this m beta and if you multiply this, you'll get an identity matrix. So that's why it's coming like this. And so kinetic energy will be just this. Similarly, for potential energy, if you do it substitution, you will see that this particular matrices will give a diagonal matrix, and diagonal terms will be square of the natural frequency of the system. So basically, you'll get the diagonal terms, and you'll get the natural frequency squares. So, but this is a very specific example. How the beta has come, we'll see in the next chapter. They are actually eigenvector of the system, which we'll be solving in the next chapter. So directly, once we have such transformation, we can get the, we can see that now we are getting the equation of motion something like, because this is, there's no coupling term, so we'll get eta 1 double dot plus the natural frequency square eta 1 is equal to 0, something like that. So very simple equations we'll get using such transformation. Okay, so if you have any question on this, you can ask. So this was background for the basically new chapter, which will be dealing with the normal modes of for discrete system, in which because till now whatever we have described using the principle of Hamilton principle, or whatever we are able to obtain the equation of motion. That's all. We are not able to, still we are not solved the equations. The equations we are keeping in a matrix form. So now with this background, we will able to go for the solution of those equations. So first, the foremost thing will be to convert those equations in the so-called eigenvalue problem, or the characteristic form of the equation, in which we will find the natural frequency of the system. As we are dealing with the multi-degree of freedom system, so the procedure, whatever we'll be describing, will be in the form of matrices. We are keeping the equation of motion in the mass matrix and stiffness matrix form. So while writing the equation, then again we'll not write the expanded form of the mass matrix and stiffness matrix. The procedure can be described by a very compact form of the mass matrix M and K, and we can able to describe the procedure. So that will be the next chapter. So I think there is no question on that, no issue. So I think now we are ready for the solution of the multi-degree of freedom, the eigenvalue problem, or the so that is nothing but before solving the force vibration, we need to solve the natural frequency of the system and the eigenvector, that is nothing but the mode shape. And mode shapes, as we have seen, can be used for the transforming the equation of motion in the normal coordinate system or the natural coordinate system, where the equation becomes uncoupled, they become simpler. Okay, so that will be the next thing. And regarding tomorrow's quiz, so at 5 o'clock, I think, so maybe you can come early by, or maybe I think if your class, we can start at 5 o'clock only. So I will send an email, and in that the link will be there. So once you click the link, I think you will see the objective type questions, and keep your some rough paper and pen, pencil, whatever, so that if some small formulation you need to do, you should able to do that thing. And yeah, so that is the information regarding the quiz, and that will be for 1 hour. And you need to submit at the end. So there is a submit button at the below. Once you complete your all answers, you must submit. Otherwise, it will not come. It will not be coming into the portal. Okay, you must submit before you leave that particular site. Okay, so I think I'm now stopping here. So all the best for your exams tomorrow. And then I think coming Friday we have holiday. So Saturday I think we'll be having class. Okay.